An autonomous vehicle cruises down an empty road. Suddenly, it slams into an emergency stop. The detected threat? A perfectly flat, safe metal manhole cover. To understand why this happens, we have to look past standard mechanical failures. The vehicle's brakes didn't lock up, the onboard computers didn't crash. The algorithms processing the sensor data and the software actuating the brakes executed their compiled instructions exactly as programmed. Even the radar sensor itself worked flawlessly, transmitting and receiving radio waves in strict accordance with the fundamental laws of physics. For decades, automotive engineers relied on the ISO 26262 functional safety standard. That framework is designed to hunt down broken hardware, degraded wiring, and software bugs. But ISO 26262 cannot account for this manhole anomaly. It has no mechanism for handling a situation where a sensor operates perfectly, with zero faults, but is pushed to its absolute physical limits. Autonomous systems require us to confront a difficult reality. Flawless component execution can still yield hazardous behavior. This specific vulnerability is why the industry developed ISO 21448, commonly known as SOTIF, the safety of the intended functionality. It addresses hazards that occur without a localized component failure. SOTIF operates on a specific mapping objective. It forces engineers to actively search the operational environment for unknown unsafe edge cases and shift them into the known safe domain. The mathematical bridge for this shift is Clause 7, specifically the acceptability evaluations in 7.4 and the documented work products in 7.5. These clauses translate abstract environmental variables, like heavy rain and metal manholes, into strictly quantitative validation parameters. While legacy workflows focus on how long a component will last before breaking, SOTIF requires engineers to predict exactly how a functioning system will misinterpret a complex environment. The method is rigorous. You isolate the physical sensor limit, define the exact environmental trigger, and calculate the statistical probability. SOTIF uses mathematical logic to validate when inherent physical sensor limitations are safe enough for deployment. Under Clause 7.3.4, SOTIF defines these physical limitations as functional insufficiencies. This is distinct from a software bug or hardware degradation. A functional insufficiency is simply an immutable limitation of the technology itself, strictly dictated by the laws of physics. Take the radar sensor as our anchor example. Radar is vulnerable to multipath propagation when interacting with metallic objects. The sensor emits a radio pulse, but instead of bouncing straight back, the wave reflects off the asphalt, strikes a metal manhole, deflects into the vehicle's undercarriage, and finally returns to the receiver. Because the radar calculates distance based on the time of flight, this multi-bounce delay forces the algorithm to generate a false distance metric. The code does exactly what it's supposed to do, but it projects a solid ghost target directly in the vehicle's path. Every sensor modality has these physical constraints. While radar struggles with multipath reflections, a camera's optical dynamic range will collapse when transitioning from a dark tunnel into bright sunlight. But the insufficiency is only one half of the equation. The second variable is the triggering condition waiting out in the operational environment. A functional insufficiency is dormant and mathematically harmless until it is activated by its specific environmental trigger. Only when the radar's multipath vulnerability aligns with the physical layout of the flat metal manhole does the system generate the hazardous ghost braking event. Engineers cannot alter the laws of electromagnetic propagation. The physics dictates that these false positives are mathematically certain to occur over the life of a fleet. This reality brings us to Clause 7.4, the acceptability evaluation, and the philosophical pivot mandated by the standards Note 5. The logic tree illustrates a shift toward probabilistic mitigation, acknowledging that the underlying physical error cannot be eliminated. Engineers measure this probability by calculating the residual risk. They evaluate three precise factors: the severity of the hazard, the controllability for the human driver, and the exposure, the frequency at which the vehicle will encounter that specific trigger in the real world. To determine if that resulting risk calculation is acceptable, ISO 21448 utilizes global safety benchmarking frameworks. A primary metric is the minimum endogenous mortality, or MEM. MEM establishes a hard mathematical ceiling. It demands that fatalities induced by the technological system fall well below the natural mortality rate threshold of society, typically quantified as less than 10 to the negative fifth deaths per person per year. The engineering objective is to suppress the false positive rate below the MEM threshold through rigorous statistical tracking. If the calculated residual risk of a manhole breaking scenario exceeds that acceptable target, the system architecture itself must be changed, initiating the mitigation loop defined in Clause 8. Rather than attempting to redesign the radar physics, engineers implement architectural mitigations. They might mandate camera sensor fusion, requiring optical cross-verification of all radar targets before the braking code is allowed to actuate. Clause 7.4 transforms an unfixable physical error from an engineering dead end into a mathematically bounded risk variable. The framework of Clause 7.4 is formalized into rigid, quantitative work product matrices in Clause 7.5. These matrices serve as proactive engineering specification sheets. This table, the Clause 7.5.1 database, catalogs every identified functional insufficiency directly alongside its environmental trigger. It records precise parameters, mapping out vulnerabilities like a metal sign positioned at a height of 4.5 meters at a distance of 50 meters. These exact environmental measurements define the physical boundaries of the vehicle's operational design domain. Next is the Clause 7.5.2 Acceptability Evaluation Report. This document pairs each physical insufficiency with its required probabilistic safety threshold, linking a radar multipath anomaly to a target rate of less than 10 to the negative 7th per hour. That specific matrix row locks in the formal, quantitative pass or fail criteria for the entire autonomous platform. These matrices map out exactly which specific edge cases the system is most vulnerable to in the real world. By doing so, they remove subjective engineering opinions regarding what feels safe, replacing them with statistical absolutes. Clause 7.5 matrices represent the exact mathematical threshold where a system transitions from an unacceptable danger to a road-legal product. Those specifications authored in Clause 7.5 directly command the system validation testing executed in Clause 10. The derived parameters from the matrices dictate precise fault injection vectors within high-speed software-in-the-loop environments. Here, the digital vehicle runs thousands of rapid iterations against specific triggers, like a wireframe bridge pier. Engineers use these simulations to continuously track the false positive rate, ensuring the system's reaction remains suppressed below that 10 to the negative 7 threshold. Model-in-the-loop systems take the 7.5.1 matrix and use it to deliberately bombard the vehicle's perception algorithms with known, difficult triggering conditions. These same parameters translate directly out of the simulation and into the physical world, dictating the design of proving ground scenarios. The matrices tell the test track operators exactly what to build. If the database flags a camera vulnerability, engineers might deploy an artificial rain system that produces exactly 20 millimeters per hour of precipitation over a specific target. Both the physical and simulated verification stages are entirely reliant on the mathematical precision of the targets generated in Clause 7. Validation is rarely clean on the first pass. When a real-world or simulated test fails to meet the acceptability criteria, SOTF provides a strict feedback loop. A verification failure indicates the discovery of a previously unknown triggering condition, one that the current system architecture cannot yet handle. This failure routes the engineering team back to the beginning of Clause 7. They update the parameters and initiate new Clause 8 hardware and software mitigations to address the gap. The SOTIF 7.5 work products represent a living statistical model of the system's operational reality, evolving with every mile driven. Building an autonomous sensor that never makes a mistake is an engineering impossibility. Physics will always intervene. True safety in autonomous driving isn't achieved by eliminating physical limitations. It is achieved through the rigorous, mathematical bounding of those limits.